Hi, good morning, everyone, and welcome to the Go Fly lecture. We're really excited that you could join us this morning for Bruce Kay's lecture. As a reminder, Go Fly is sponsored by Boeing, and we're also joined by a number of great partner organizations who are helping along in the Go Fly prize journey. This morning, we're really excited to welcome Bruce Kay, who's a retired Sikorsky Tech Fellow for Air Vehicle Design. He was responsible for changing the paradigm that helicopter airframes had to be metal. He conducted requisite R&D and then became chief engineer for the world's first composite airframe helicopter, the Sikorsky S-75. Subsequently, he was appointed chief of design for the Comanche helicopter. Following first flight, he returned to research and managed Sikorsky's advanced airframe R&D. This included pioneering applications for advanced design concepts, analysis, producibility, and software simulation tools. He retired as a Sikorsky Tech Fellow for Air Vehicle Design, and the AHA also awarded him with a fellow status. After retirement, he consulted for Sikorsky on the CH-53K technology insertion, consulted for DARPA on composites, ONR, and aerostructure suppliers. He's currently co-authoring a book on the Comanche helicopter development, and Mr. Kay has received numerous recognition awards from the AHS, the Army, and NASA. He's presented over 34 technical papers and holds 6 patents, and we're really excited to have Bruce with us here today. We're really looking forward to his lecture. And with that, Bruce, I'll turn it over to you.
Okay. Share screen. Okay, thank you, Paul. Today, I'm going to talk about air vehicle design and project management. I've been very fortunate to have worked both on product design and as well as research and development, and I've gone back and forth between the two areas. I've worked on more than a dozen different aircraft projects over a period of 50 years. I've been principal investigator in approximately $100 million of research and development programs for the government and company projects over a 20-year period. And I've overseen over 50 design and process innovations, new techniques that were never used at Sikorsky. This gives me a unique vantage point to talk. I've experienced both the thrill of victory as well as the agony of defeat, so I can share some lessons learned with you. Thank you. The Go Fly contest really has a dizzying array of concepts. I've just put up a few here, but what I fully expect is that this contest will result in some very new disruptive technologies in the area of personal transport. But that's not what I'm going to talk about today. Instead, I'm going to discuss the nuances and pitfalls that are associated with air vehicle design and project management. Let's start with the requirements. It's a contest, so it's fundamental that you follow the rules, and the rules define the vehicle size, the noise levels, the speed, and of course, safety. The drivers for noise is a function of the lift and the propulsion system that moves you forward through the air, the power that's required, the speed, and of course, weight. And I put weight in red because that's what I'm going to be talking about, as opposed to the aeromechanics or flight science. Performance also is a function of lift, drag, power, and weight. I think it would be very wise to establish early on the attribute partial derivatives with respect to weight. For example, I remember working on one project and that derivative was very simple. 1 pound of weight equated to 1 foot per minute in vertical rate of climb. It's also pretty handy to develop parameter sensitivity relationships between all of the different parameters or attributes relating to one another. This will give you the knobs to turn later on as you're doing trades and you have to adjust something to meet the overall requirements. So knowing the sensitivity relationships will be very important. This all comes down to a balanced design. What you want to do is balance the performance, which are the flight science opportunities. That's where you're going to achieve the breakthroughs, but don't lose those achievements by blowing it on weight or integration factors. This chart kind of says it all. This is a summary of the whole program in reality. On the left-hand side of the screen, you have the score, and here, noise, size, and speed. And you look at the score relationships, and obviously noise is the most important. Noise is affected by the acoustics of the system, which the contributors will be the lift system and the power plant, propulsion system. You should know what the expected values are, or you'll be taking guesses up front when you start conceptual design. So you could put in the expected value, and then you have a potential variation. How big a variation do you think it will be? And then what are the risks, or what do you have to do to get to where you want to go? I say potential variation. If you drop down to propulsion system here, let's say you pick an existing engine or motor. You know what the expected value is because it's been in existence. The potential variation will be small, and there'll be no risk because it's an off-the-shelf commodity. So filling in this chart up front kind of gives you an idea of where you're going to go, and it's very important. And the scores will range from 0, if you don't achieve anything, up to 8.65. And I'd like to see the 8.65 in this contest. I can't wait to see that one. Well, so I say system integration. What happens? There are system losses. The lift system can you can lose lift. You can have a perfect system, but then you have dirty air going in, or during a maneuver it stalls. So there are system losses that you have to contend with. If you have an air-breathing engine, reciprocating or jet, there are losses associated with the air inlet and the exhaust. Gearbox can have frictional losses. There are also temperature and altitude effects. There might be cooling requirements that can consummate power or cause drag. Engines, gearboxes, electric motors generate heat. And if the pilot is in an enclosed compartment in a hot day, you might have to pry out a window, all of which causes momentum losses. I put up here a chart of a recent utility helicopter that we worked on. Excuse me. And it's a weight breakdown. You're going to have your own weight breakdown, but the important systems, the biggest systems are going to be certainly the lift system. Here I've just shown a rotor, but it can be anything. It can be a fan, jet. Propulsion is pretty heavy. If you have gearboxes, transmissions, they're heavy. Airframes tend to be the heaviest. And then you plot it out. And what this will do when you make up your vehicle, it shows you here's the areas that will give you the biggest bang for the buck when you're designing them. So it's a convenient chart to look at, and it tells you where you can get in trouble. Let's talk about turning. It's a race. The shortest distance between 2 points is a straight line, but that means you have to accelerate and decelerate and then turn around the pylon. So a more practical way is certainly an elliptical course or a circular course. But when you're making turns, increased power is required and you have higher load factors. The Comanche helicopter was designed for a 70-knot sideward flight. That's pretty fast. That's as fast as some small helicopters go in forward flight. And it had to make a 180-degree yaw turn in a 45-knot wind, which is it's a gale, it's a storm. So it moves pretty fast sideways. That's pretty nice. But the maximum continuous horsepower rating for the fantail with over 900 horsepower. So it takes a lot of power to make a sharp turn. Loads. You're going to have to develop your own loads, all of them. They have to be developed. The flight maneuver loads, which includes turning, landing loads, both hard landing as well as crash landing. Uh-oh, I got something that says my internet connection was unstable. I hope I'm still okay. Crash landing loads are required for safety. Things can go wrong and you need to be able to land safely when that happens. And of course you have vibratory loads which are which will affect your fatigue strength of the components. I expect that this will be a small, lightweight vehicle. Shell structures, if you have them, could be very lightly loaded, and minimum gauge thicknesses could prevail. I show as an example of lightweight structures two designs that were pretty significant. The Solar Impulse flew around the world. The Gossamer Albatross, which was man-powered, flew across the English Channel. Obviously, the structure is pretty lightweight. You could see through the skin. So, but very important, don't skimp on the dynamic components. The parts that are rotating subject to fatigue, you don't want to go lightweight over there. You want to make sure that those are sturdy and they can hold up to the fatigue loading, vibratory loads. Materials that you can use include composites, which are typically 15 to 40% lighter than metal. Graphite is the strongest and stiffest material. Kevlar is the lightest, but it's poor in compression. Fiberglass is a good general all-around material. Lightweight structural foams could be easier in a home-built situation than using honeycomb. I would still recommend metal for complex joints, and you can hybridize for efficiency. If you have novel composite designs, the traditional way to validate the structural integrity is a building block approach, going from coupons, elements to full size. You're probably going to use existing materials. You should use existing materials. And material, that means that when you buy the material and you lay it up, that doesn't necessarily mean you're going to get the properties, mechanical properties that have been published. NCAMP, the National Center for Advanced Material Performance, has some straightforward methods for validating that when you build a part, the strength will match the values that you're designing to. Unorthodox designs should be tested, particularly designs where there's complex out-of-plane loading. Composites are very sensitive to that. And I always recommend full-scale static or proof load testing for a composite structure. Internal loads, and there's a lot of things that can go wrong, and that's your real good check. Manufacturing. If you're using a body, the streamlined shape will likely lead to composites. Composites are easier to make than aluminum, metal. Economical non-autoclave material and processes with low cost molds, wood, or even foam should suffice for this kind of a program. If you're using adhesive bonding, a lot of caution. Be very careful. Faulty bonds that look good could get you in trouble. Quality control requirements are extremely important, which involves cleanliness and out of material surface preparations. These times can expire on adhesives, so it's very important to use strict quality control when you're doing adhesive bonding. Do-it-yourself kind of construction is possible, of course. I would refer to the EAA, the Experimental Aircraft Association, for guidance. They do an awful lot of composite home-built airplanes. Lastly, if you're going to subcontract parts to build, get your suppliers engaged early. There can be huge variations in cost between suppliers, and if you wait too long, you pay what they ask and there's no time to negotiate. So get them on board early. Dynamics. I think most people know that rotary wing lift creates vibration simply because one rotor blade is going with the wind, the other is going against the wind, and that creates vibration. So what you have to do on any aircraft that has these kind of lifting systems is you must avoid resonant natural frequencies. Watch out also for ground resonance, where the aircraft can rock on the ground and actually turn over, and it could be a very hazardous condition. After it's built, solutions for solving dynamic problems will be very heavy. The natural frequency equation is simply the square root of K over M, where K is the stiffness and M is mass. After it's built, it's pretty hard to change the stiffness. So the typical solutions are either add material to increase stiffness, you can't decrease it, or add mass, and that's carrying dead weight. Dynamic components are subject to fatigue strength. If you have rotating components with N per rev type of loading, it's important to look at the fatigue strength. Helicopter companies do extensive fatigue testing prior to flight. They also do gearbox endurance testing and then tear down the parts to make sure that there was no damage. On the Comanche, we built a dedicated propulsion system test bed to bring out the dynamic system, the main rotor, the engines, the shafting, oil coolers, tail fan, etc. I don't expect that anybody doing the Go Fly competition will go to this extreme. The alternative is simply do tie-down tests before you're ready to fly to make sure everything works together. Let's talk about crashworthiness. Crashworthiness is important because you want to avoid injury or even worse, death. So things can go wrong in the air, and if you're coming in for a hard crash landing, you must attenuate the high impact deceleration forces. Occupant restraint is important, so you have to have a protective cocoon. High mass items, anything that weighs a lot or even a little bit, if it breaks loose and hits the pilot, it can cause injury or harm. There must be means for egress to escape. You must prevent fires, fuel systems and fuel lines. There are techniques to prevent leakages on crash. Lithium-ion batteries have been known to become incendiary, so there needs to be protection there if you're using electrical power. And if you're using electrical power, I think we now have to look at the potential for electrocution in the aircraft if wires carrying high voltages or high amperatures are flaring around. The criteria for crashworthiness is mission dependent. I've worked with a number of different agencies over the years, the FAA, the Army, and the Navy, and they all have different crash criteria for certifying their airplanes. The Go Fly requirement is do not exceed 5 Gs in a crash condition. So somehow you have to make sure that the pilot doesn't feel more than 5 Gs, because that has been shown to, that's the onset of where you get serious injuries. So the factors that determine what the criteria should be would be the speed of the aircraft, the altitude that it's flying. That's the primary conditions. I put auto-rotational capability. How fast could it come down if it's something goes wrong in flight? And certainly the flight profile and vehicle configuration all go into what are the criteria that you should use to design a system to not exceed 5 Gs. Excuse me. I have to go back. But what if it's a strap-on? What if it's a strap-on where you're not climbing into an aircraft, but you're actually wearing the flight system on your back? That gets kind of interesting. Falling out of the sky with a couple of 100 pounds on your back is interesting. I don't know what the answer is. I haven't thought about that. The landing gear. Certainly shock absorbers absorb, oops, okay, I missed the slide. Crash energy attenuation. Traditional helicopters use a system approach. And the order of energy absorption is based on the efficiency. A landing gear has a very high load stroke efficiency curve. The area under the curve is very good. Helicopters also use stroking seats. These are controlled mechanisms to absorb high seat speed. The structure can also absorb energy, but it's usually a fallout capability. Airbags have also been used in certain applications. Yeah, I just said, what if it's a strap-on? We talked about that. Let's talk about the landing gear. Landing gear, besides being a shock absorber on the ground, it prevents rollover or tipping in winds or when you're taking off, any sorts of rocking back and forth due to unbalance. Should the landing gear be faired or retractable, drag is a major consideration. Bicycles, which operate at a much lower speed, racing bicycles use streamlined helmets and faired wheels. So when you're looking at the landing gear, look at the drag. I might also expect that some unconventional approaches will come out of this program. The little Hughes OH-6 was designed before the advent of formal crash requirements, and it turned out to be a very efficient aircraft for crash. The structure, the primary structure, had basically a truss type structure. The engines were mounted on the back of the truss, the pilots on the front, the rotor system on the top. It went directly to the landing gear, and it was performed extremely well in crashes prior to people having to design for crash. Composite crashworthiness. When I was doing the ACAP helicopter, the Sikorsky S-75, the naysayers said, it can't be crashworthy. How could it be crashworthy? Compare the strain energy of graphite, which goes up, snaps, and comes straight down, to aluminum. There's no, look at the difference in areas under the curve, which is energy absorption. I said, that can't be right. We could do better than that. So we went down in the shop, we picked up some composite engine cowlings, I think they were, cut them up, put them in a machine, crushed them, and we got a fairly decent load stroke curve. For the actual aircraft design, we then designed a little more rigorously structures that could absorb energy. Here's a crushed section of the lower fuselage, and we were able to show bearing failures to absorb energy in other joints. We put that into our design, and we drop tested the ACAP helicopter at NASA Langley at 38 feet per second sink speed. The dummies inside the aircraft, anthropomorphic dummies, survived the test. The tail cone broke off as intended to reduce the sprung weight on the landing gear. So that said, composites can be crashworthy. A few words on ducted fan performance. In order to get your performance, you need tight clearances between the blades and the duct. That means a rigid structure. Otherwise, you're going to hit the blades or it's going to open up. The inlet and exhaust radii are also important. Here's a close-up of the Comanche fantail. You can see there's a nice generous radius on the back end, a sharp corner on the front end, and that was based on the inflows to the fan during flight. Noise is caused in a helicopter. Rotor blades are the primary source. Everybody's heard the whop whop of a approaching helicopter. That's a function of tip speed and tip configuration. And for fans, ducted fans, you have the RPM, the blade numbers, and the stator design have a big effect on the design. As you minimize the lifting system noise, the engines and gearboxes could start dominating. So you have to really look at the whole system. Other weight empty option decisions, which you, the designers, have to decide what you're going to do. Are you going to have wheels or skids or something else? Flight controls, will they be fly-by-wire or simple mechanical systems? If you can't quiet the system inherently, are you going to have to put acoustic treatments on the vehicle? Do you build in engine starters or do you use portal devices, etc.? So these are decisions you have to make and decide. Now let's move on to project management. I'm going to talk about organization, the plan, the design process, safety, risk abatement, which is very important, and weight control. These are the skills that you need to varying degrees, but you need them all. When you start the conceptual design, you can get by with a handful of people, generalists, if you will. But as you proceed into preliminary design and detailed design, you're going to need the advice and analysis and help of specialists, because there are subtle little things that make a very big difference. And since acoustics are the highest point value in this score, it would be a good thing to have a specialist on board or consult with somebody that really does it. Wishful thinking is not a way to achieve new attributes. There's a conundrum on all of this. The conundrum is aerospace primes, the big companies, if they were doing this, they could easily spend $2 million just on design. But let's go back in history. The Wright brothers, two guys that never even went to college, did it all by themselves. So you're going to be somewhere in between, and you have to figure out what that balance is. Today we all use integrated product development teams. It's a small, knowledgeable team. All of your stakeholders and technical disciplines are involved, and make sure you get the expertise that you need. It's important. You make up a plan of performance. Everybody's got to buy into that plan of performance, which is what you're going to do. Physical co-location is preferable to virtual co-location. Virtual co-location, you have latency. It takes time for things to go back and forth. People compose letters, they don't talk. One of the most communicative programs I ever worked on, and occasionally we used to put people in the basement at Sikorsky to do proposals. We crammed them in like sardines, but boy, you could communicate like crazy. You could smell a problem across the room. You knew what was going on. Management, by walking around, you just pick things up through the air, through osmosis. You don't get that with virtual co-location. So if at all possible, I strongly recommend physical co-location. In any case, you need standing meetings, and the standing meetings are to assign actions. You got to do this, you do that, and you come back and you report on it. You don't solve your problems in these standing meetings. You go off and do those on the sideline, but you've got to have progressive meetings to assess where you are. Problems don't get better with age. Be careful of letting things fester. Commitment versus denial. I want to just say a few words about that. It's important. Commitment is working hard to a dedicated end. That's good. Everybody does that. Denial. I'm not talking about lying. I'm not talking about lying at all. I'm talking about denial in the same sense as trauma. Something bad happens and people go, oh no, it's not happening, it's not real, and they go on. I had an incident where we had, it was right after I retired. I was a workaholic, and I said, hey, I don't want, there's more to life than just work. So I'm going to cut back to 24 hours. I came back as a consultant to Sikorsky. We were working with a small company on the other side of the country, developing some really new, radical manufacturing process approaches. And they were having trouble, but they were working hard. Really smart engineers, hardworking, really good people. Then they got kind of into another problem. I had to go out there. I did a deep dive. And lo and behold, they were violating the laws of physics at that point, and they were denying it. They just didn't recognize that they couldn't get to where they were going. At that time, the recovery was so big, the company went bankrupt. Sad. The operation, for IPTs, you need a strong, dedicated leader who sets the goals and the agenda. The rules are certainly seek consensus. Listen to everybody. The loudest voice should not prevail. Timely inputs, extremely important, because other people are working based on those inputs, and late inputs or false inputs can destroy the whole team. It's not a democracy. Sorry, it's not. The leader has to make decisions and move on, and a weak decision, particularly when minutia is involved, is often better than no decision. You don't let people wander around the abyss. The IPTs can be confusing at first. There are natural enemies that show up. Who are the natural enemies? I could think of a lot, but and cats don't get along with dogs. They've been trained that way. The weights engineer wants to make things light. The structures engineer wants to make them strong and heavy. There are messengers. His job thinks, well, I'll come to the meeting, I'll take notes, and I'll go back and tell somebody else, and he'll decide. No, you want the decision maker at the meeting. Some people are too meek. They don't know how to speak up. You have to draw it out of them. Other people say, oh, I got better things to do. I know what I'm doing. Well, maybe, yeah, but other people are counting on your inputs. Some people say, well, they didn't have anything to do with me this time. Why am I here? So if you have people that work in a team, that's great. But if you're drawing people that have come from large bureaucratic engineering organizations, it's a problem. And on Comanche, we had to actually dedicate some training. When I say training, I don't necessarily at this point say send people to school, but you really want to get people to understand structured problem solving and conflict management, so you don't end up with people getting personal and getting visceral attitudes towards each other. So let's talk about the plan. The plan includes the research, the design, the analysis, the experiments. Very important. Experiments trump analysis any day of the week, the fabrication and the test. You start with an air vehicle specification, which are the requirements. You flow them down to the parts and systems. You need a budget and schedule. The budget and schedule must identify the resources. Engineers hate schedules. They do. They say, leave me alone. Let me just do my thing. I'm sorry. You need a budget and schedule. Otherwise, you're going to wake up one day and you're going to be out of time. Time is your enemy. So you must manage your budget and schedule religiously. It's a fact of life. What do I mean by a surge capability? There comes a point where suddenly you're going to find, as you get to the short strokes, you're working 24/7, 80, 100 hours a week. So if you start out that way, or if you're counting on that, if you're not counting on that, that's why it's important to manage the schedule, because eventually you get to a point where there's not enough time to do the work. You just can't fit it in. I included a marketing plan here. Why did I do that? We're not selling this aircraft, we're running a contest. I perceive that most of the contestants in this program are not big companies with deep pockets and deep benches. So you're going to need staff buildup. You may also need sponsors to help build parts, which get kind of expensive. So the way you do that is you have your concept, and you have some data that says this is a good idea, and you can actually attract people who want to jump on a good thing as you go forward. So a marketing plan to handle those contingencies, I think, is an important fact, unless you somehow have this team already. Track your allocations for attributes. It's important. You don't want to wake up one day and find out, uh-oh, we don't miss the requirement. We got a 2 in this instead of a 4. Definitely plan for multiple design iterations. The design will change, and you better have a management reserve in your plan for budget, because things will go wrong, and you've got to handle that. So the first step is research. You want to gather data from existing small VTOL aircraft, look at the performance, the weight, power, Why do you do this? Because you need it for the preliminary design parametrics. You want to do sanity checks against your calculations. You'd like to do competitive assessments. If you're doing something that other people have done and you're doing the same thing, you're not going to win. So it's important to kind of gather the data on what's been done so far, develop some parametrics. Synthesis is going to be necessary because it's going to be very nonlinear. I don't think you're going to find what you're doing because nobody's done it yet. And parametrics are a lot easier to use to conduct trade-offs than doing bottoms-up design. Lastly, review the FARs, the Federal Air Regulations. The FAA has to grant you an airworthiness certificate, but more importantly, you want to look at those regulations because within there, there's a lot of relevant rules and design practices. And I'll bet that when you look at, if you haven't, and you look at it and you can say, oh, I didn't know that, but you do need to know that. And they deal with safety, of course. You then go to make your general arrangement drawing, simple general arrangement drawing, inboard profile for packaging. You start out with your best available knowledge. You're not going to know everything, but just make the drawing. It's needed to support your analysis. You do your rough sizing. It's one thing to kind of say, well, parametrically this works, but I don't think you have parametrics. So volume times density tells you what the part weighs. And as you go forward, you add progressively more detail. Safety. A number of speakers have already talked about FMICAs, failure modes and criticality analysis. Can the part fail? If so, how? And is that critical? Crashworthiness, I've talked about. Single point failures. You certainly want to minimize that. How do you avoid hazardous single point failures? You need backup emergency power, redundancy, fail safe, safe life. Safe life is like for dynamic components, conservatively you might design to keep the stresses below the fatigue endurance limit to get a very strong design. Right now, people are focusing probably on the air vehicle, but pay attention to the flight controls. Single point failures there can be catastrophic. If you have no control over the aircraft, it's going to crash. Risk assessment. For the number of years now, people have been using technology readiness levels to define risk. Technology TRL 0 is an idea, and TRL 5 and 6 is where you're going. You want to apply this concept approach to the system, the components, and the parts. By definition, TRL 0 to 4 is risk, and that's where you guys are, because otherwise it's been done and there'd be no contest. And TRL 5 or 6 is where you're heading. I don't believe that anybody has mature technologies that currently meet the go-fly criteria. Pragmatic risk reduction. During preliminary design, you have data. You want to know the credibility of the data, and you'll have supplier inputs. So caveat emptor. As you get this data, trust but verify. You have tried and true versus novel approaches. The novel approaches, experiments and tests are the best means of validating that your approaches work. Have backup plans with alternative designs. Watch out for, there are knowns, there are unknowns, and then there are unknown unknowns. You don't know what you don't know. How do you handle that? Independent oversight. I suggest that you have preliminary and critical design reviews. Preliminary design is right prior to starting detailed design, and critical design review is before you build the aircraft. Non-advocate deep dives are very important, and you have peer reviews. I want to just divert for a second, a war story. I said I would talk about agonies of defeat. There was one project that we were developing a new manufacturing structural design concept. We went through the building block approach. My structures engineers signed off on it. They showed it to me. I said, yeah, that looks good. Let's go ahead. We had critical design review, which was perfunctory, but a lot of people there. Government was there. Everybody said, yeah, go ahead, build it. They built it, tested it, and it failed catastrophically. This bothered me tremendously. I said, what could I have done differently? We followed the book. The only thing I could think of that I could have done differently was to call in another peer, somebody that I respected, because once we looked at the failure, we said, oh yeah, it was hindsight, it was easy, obvious. But if I would have had a peer, another peer, independent, non-advocate, wasn't for it, coming in off the street, so to speak, look at it, I think we would have succeeded and we could have fixed it and not had a failure. So who do you get for the peer review? Eventually, you're going to have the airworthiness authorities sign off on it. So as much as you can, get them. Subject matter experts, industry friends or alumni that you went to school with and are now out in industry work, college professors, gray beards will help with war stories, GoFly mentors and consultants. You got to pay for them, but you want oversight. If you got something that's coming out that's too good to be true, I think it's important to kind of get some independent assessments. And then you could fill out the risk cube where you've got high risk, high probability, low risk, low probability. I just want to kind of end my presentation talking about how things have changed, how things were. I started my career at Sikorsky on the S-61 HSS-2, good aircraft, still around, still flying presidents of the United States. That was a traditional helicopter configuration. We used rules of thumb design prevalence. It had very stable attributes. Once it came out of the preliminary design, the loft lines, for example, were scribed literally into big aluminum plates, and you traced them from the plates. It was very difficult to iterate. There were no computers. So you had functional engineers that were basically stovepipes. They just bent their heads down and did their thing. The next aircraft was the Blackhawk, the H-60. That had significant but incremental improvements. To handle those improvements, the parametrics for weight and performance were adjusted with very carefully with technology adjustment factors. That aircraft actually the prototypes came in underweight. It had new crashworthy requirements, and for that we hired a crashworthiness consultant, happened to be, I still remember him, Dr. James Turnbow from the Arizona State University. He was the guy that wrote the design criteria for the Army, and he helped us immensely. And what happened, good thing, what happened during the competitive fly-off against the Boeing UTAS, the helicopter had to make a crash landing in a forest. It was survivable. Everybody left the aircraft. It damaged the trailing edge pockets of the blade, and it flew out within a couple of days after they chopped down some of the trees. It would have otherwise been catastrophic. So things happen, and prepare for it. The last aircraft that I want to talk about is the Comanche. It was a very advanced, sophisticated helicopter, the most advanced, sophisticated helicopter ever built. It was done with integrated product development teams, computerized designs. And I remember when we were starting design, program manager came to me and said, hey, Bruce, you got all these fast computers. Are you going to do it faster? You know what happened? No, you didn't do it faster. You did it better. You did more designs, more iterations, but be careful. You can go crazy with computers, finite element models. People go overboard with elements and it takes forever to run. You got to be a little practical with that, but computers have really come a long way. It had extensive, challenging, often conflicting performance and technical requirements, high speed, high maneuverability, low radar, low IR signature, internal retractable weapons, packed with avionics. It was very complex, difficult to predict interactions, and there was requirements creep. Be careful of requirements creep. That's where you say, oh, we can make it better by adding this. Yeah, you never get done. That aircraft had an ongoing weight closure battle. When the program was canceled for other reasons, there still were weight problems. So here's where you're going to end up. I think depending on your payload fraction, you're going to be somewhere between empty weight, 200 to 800 pounds, and you got to fit all of this stuff in. So that goes back to my first couple of charts where you make it lay out what the actual weights will be. Weight control is important. Close monitoring is mandatory. Provide a margin for growth as a function of time. Watch the center of gravity. Ballast corrections, if you have to do them to balance the aircraft, can be very counterproductive. So, in summary, pay attention to all your attributes. Go for a balanced design. Make a good plan. Be realistic, knowing what you know and what you don't know, and get help when needed. And I have one more slide. I was extremely inspired by the Olympics closing ceremony where they took a mass of 300 little UAVs and flew them into the Olympic symbol. And they did some other displays. To me, that says that Intel and companies like that are well on the way to developing an infrastructure that could handle personal transport. So it's up to you guys now to develop the personal vehicles. So good luck, and I'm now open to questions. Thank you.
Great. Thanks so much, Bruce. I got a couple questions coming in here. We'll just get them collated real quick. Great. So do you have any advice for competitors at GoFly who are trying to source parts for their builds in terms of being a pretty small player and working with people to get the right parts?
Yeah, do it early. I mean, I said that before. Do it very early. If you know you want to go to small shops, probably. Again, I'd advise talking to the EAA, the Experimental Aircraft Association, for guidance. They do this all the time, so they could probably point you in the right direction.
Great, thanks. And then what's your opinion about using wood for home-built projects, plywood and spars?
It could work. I mean, there's a lot of wooden airplanes flying around. Wood went out because aluminums and composites are much lighter and much more durable. If you look at the home-built industry today, I think most of them are aluminum and composite. Wood will work, yeah. I mean, there's a lot of airplanes that fly with wood.
Great. And then do you have any recommendations for the best way to simulate the acoustics of a flying concept?
No. When we did Comanche, I showed that chart of all the skills, and we had one guy, I'm not going to mention his name, who gets swamped. He did all the acoustics. He was really very good. And he did it on a part-time basis. That's a hard one. Simulate? No, he wasn't simulating things. He was doing a lot of analysis. He was doing tests where he was listening to different vehicles. And when we were building up the Comanche during tests, he would have microphones to measure the acoustics.
Great. Do you have a sense of what sort of weight reduction might be possible by using electric motors?
No. No, I don't. There's an awful lot of electric powered vehicles flying around today. I think it's very mission dependent. I mean, the Go Fly mission is to fly the between the pylons, make some touch and go landings designed for that. And I think that's why I say do some trade-offs. Look at what's been done, and then say, okay, here's what we need to do for this particular mission. Sure.
And then you spoke about rotary wing aircraft a lot. You know, that's your background, of course. But there's potential for other propulsion systems to be in play here as well. What do you think about the sort of trade-offs between what options are out there?
Yeah, absolutely. I think most of the vehicles that I'm seeing now, and it seems like they come out one a week, are varieties of electric motor powered vehicles, fans, little propellers. I think you just got to do the trade-offs. To meet the Go Fly requirements is going to be challenging. I don't think there are any little helicopters by themselves that do it. So you've got to be innovative.
Sure. And then given the size and scope of Go Fly, do you have any particular thoughts or advice about things to think about when choosing adhesives?
Be very careful. Be very careful. Adhesives can look like they're adhering things. There's a term called a kissing bond, where you do a coin tap and it sounds good because it's holding together, but it's like holding together like spit. There have been literally millions of dollars spent by the industry to detect weak bonds. The Navy on some recent aircraft said you could use adhesive bonding in primary structure as long as it fails, it could still carry load, which meant that you had to have backup fasteners to carry it. So adhesives, you really have to be very, very careful on the quality control and the process control.
Thanks. And then what are your thoughts on sort of hybrid type vehicles, things that might look like a helicopter that has some lift wings that go along with it? Any thoughts about those types of vehicles?
I think that hybridization is going to, it'll be some sort of a hybrid, I think. The wings can unload the other systems. So, but you've got to do it all within 8 feet.
Great.
Eight
and then
8.5 feet.
Yeah. And then you talked a little bit about fatigue testing, but do you have any advice for smaller Go Fly teams that are doing that with limited resources?
Yeah, the dynamic components, and by dynamic components, I'm referring to anything that's subject to vibratory loads. Usually it's the lift system. If you got rotating components that are flying into the wind, it creates vibration. I would design to keep, I think to be conservative, you want to be under the fatigue endurance limit when you do the stress analysis. And then you want to do some ground tests, tie-down tests, and it would be a good idea to put strain gauges on to make sure that the loads are what you were designing to.
Great, thanks. We'll just wrap up here with one final question. Do you have any parting words of advice for those competing in Go Fly? Anything that's you want to leave the competitors with that you think is the most important thing for them to think about as they're competing in Go Fly?
Unfortunately, my theme is a balanced design. For a vehicle that's going to fly, you have to meet all of the attributes. You optimize for certain scores. Noise is important. the tendency is to go for speed, but speed gets a very low score. So it's making the aircraft small. And again, my advice that I emphasized is try to get peer reviews, because I think you're going to need a novel approach, and you don't want to find out when you're flight testing it that something is awry, that you could fix early on. Develop your sensitivity factors so you have the knobs to turn as you go through the design.
Great. Thanks so much, Bruce. We really appreciated your time and knowledge here today. So I'm sure the rest of the GoFly community did. So thank you so much for your contributions and lecture today. It was much appreciated.
Okay, thank you. Bye.